So 6.8 is all about transforming polynomial functions, and we're going to talk about how to transform functions and how to recognize transformations when they occur. But what I really want you to be thinking about in the back of your mind is, when will a transformation impact the number of real zeros of a function? What impact can a transformation have on the solutions? How can it change those? And as we start to look at the graphs, I'm hoping you'll be able to see some of this. But before we get started, I need you to do a little throwback for me. I want you to think about this chart that I gave you a while ago. I want you to remember that chart. How to do transformations for any type of function. Okay, I hope you have this chart. It was copied on a blue piece of paper, and it should have had a lot of great information for you, because it basically tells you how to do everything that you need to do. Okay, that's my hope that you have it. If you don't have it, you'll be fine, but this will definitely facilitate your work a little bit more. Okay, so let's look at 4 examples. And as we do those 4 examples, be thinking about this chart. First one, a couple quick examples. X to the 4th plus 2. The first translation I want you to do is up 3 units. Okay? So, up 3 units, what we need to be thinking about is f of x, and then we're going up 3. So this is our function here. This is our f of x. And so we're going to take x to the 4th plus 2, and we're going to add 3 units to that. We're going to add 3 units there, and that's going to help us get our solution. So our new translated function, the new function after translation up 3 units, is x to the 4th plus 5. Okay, that's not too bad. That's not too bad. Okay, let's go left 1 unit. When we go left, we do f of x minus negative 1. So we think of f of x plus 1. Now, our f of x is x to the 4th plus 2. X to the 4th plus 2. X to the 4th is now going to have an input of x plus 1. That is a great way to write this function. You could plug that into your calculator and graph it. However, if you're feeling daring, you could go full expansion on it, full polynomial expansion. This one wouldn't actually be too bad, because that second number is a 1. There's no other coefficients or anything like that. And of course we got that plus 2 tacked on the end from before, from that original function. So really, if we go left 1 unit, here's how the polynomial changes. Right here, this is the same as that, just written a little bit differently, just fully expanded out using Pascal's triangle and binomial expansion. Left 1 unit changes the input. Okay? Reflect across the x-axis. Now, across the x-axis means we make it negative. So we're going to take our entire f of x and we're going to make it negative. So instead of x to the 4th plus 2, it's going to be negative x to the 4th minus 2. So that's the new equation after it's been reflected across the x-axis. Then vertical compression by 1/2. That means we do 1/2 times f of x. So we do 1/2 times x to the 4th plus 2. 8. X to the 4th plus 2. Do the distributive property. 1/2 x to the 4th plus 1. Right? Because 1/2 of 2 is 1 after we do that distributive property. So that's saying we've compressed this graph by 1/2. That's just a lot of plug and chug, right? Plug it in. What exactly does this transformation mean? How do we represent that with math? Up 3 units, that means I add 3. Left 1 unit, that means I go inside the input and move it left. Reflect across the x-axis, well, that's going to be a negative, right? And then vertical compression, of course, we use the 1/2 and do the distributive property. Okay, so that's kind of what we're doing on how to translate. Now let's look at a little bit different example with that. So we're going to take a second look at a different example, or a look at a second example. There's two other examples I want to show you real quick. And these other two examples, you're given f of x equals x to the third minus 4x squared plus 2. And then you're given g of x, and I want you to graph g of x and tell what transformation is occurring. Okay? So in this g of x, what we've done here is we have f at 2x. Okay? So what we're going to do is we're going to take our function, and it's everywhere we see an x, we're going to put that 2x. Here's what I mean. Let's take and plug in 2x here. Now we can clean this up a little bit. 2x to the third is actually the same as 8x to the third. Minus 4 times 4x squared plus 2. So I got 8x to the third minus 16x squared plus 2. That is the new g of x. Now if I get that graphed, let's take a look at what happens here as we're graphing. Okay, we see that we're inside the parentheses, so we're hoping it's something horizontal. Let's take a look. Escape, come on. There we go. Okay, so I'm going to go full Desmos on it. Now, I have the other one already previewed, but in red is the graph we started with. In red is the graph we start with. I'm going to zoom out a tiny bit. There we go. That's our starting graph. Now, I'm going to make in blue right now, this is my new function. Look what's happened here. It hasn't gotten any taller, right? This still comes up to here, and this still goes down to the same level down here. But what we've done is everything has been squished, right? It's half the size it was before. Instead of being at 3.87, we're halfway there at 1.93. Instead of being at, oh, where's my red graph? At 0.66, now we're at, in the blue graph, 0.33. It's kind of cool how that works. It's all tied to the fact that 2x right there. What that 2x does, and that f of 2x, it tells us, hey, guess what? I'm compressing by half. Right? I'm squishing it in halfway horizontally. Let's look at that second one. F of x plus 4. This one's a little bit easier to work with, right? This f of x, totally the same as this f of x up here. I'm going to add that plus 4 on the end. That makes this one pretty easy to look at. Here's our new function. There's our new function. So if we go to Desmos, or whatever graphing calculator you're using, let's get this new function. Oh, that's totally a 4. That's my bad right there. Let's get that graphed. So I'm going to go to Desmos. I'm going to turn off this one. I'm going to turn on this one. That looks like the function we just found. Now look at the shape. I'm going to turn that graph. The shape is almost exactly the same, right? They follow, I don't want to say parallel, but they follow the same path, okay? If I zoom in, you can see it even more. Look at, they follow each other almost exactly. The only difference is, here I'm at 2, here I'm at 6. Here I'm at 7.9, here I'm at oh, where's my 0.789 on the x? If I'm at 0.789 here, close enough, it puts me exactly on 4 because I've moved up 4. Okay? So everywhere along this graph, my y value is 4 more than the x value, or than it is on the red graph. So the green graph is 4 more. The y value is 4 more. Now I'm butchering that a little bit, but what I'm trying to tell you is that this plus 4 right here, this actually represents translation up 4. And we can see that from the fact the way the graphs were drawn. So right here, this was up 4. Here, this was a horizontal compression. Why horizontal? Because the height of everything didn't change. And then it was by 1/2. Okay? So the process here that we went through was we wrote the new equation. We graphed both. We compare. Then we make an intelligent statement. Right? After we graphed that second one, our intelligent statement was, hey, my graph has moved up 4. Some of you saw that instantly, but graphing it does definitely help us see it a little bit better for ourselves. Okay? So being able to plug into your calculator, being able to do all of those things is really going to make this easy. The other thing that's going to make this easy, I'm going to throw back real quick. Maybe. I'm going to throw back is having this, right? That's really going to help you with the writing, and it's going to help you a little bit with the identifying. So please make sure you have that. Hopefully have it out in front of you. It hasn't gone away. So you're like, I wish it would go away, Ms. Visto. I know, but it hasn't, and so you still need to be able to work with that. Okay, that'll make this step easy, and that'll help you with this one as well. Okay, make it happen, people. I know you can do it. Okay, really quickly, going back to that question we started with, did any of these change the number of zeros? Okay, no, not really. We still had lots of real zeros. I'm going to show you a different example. Here's x to the 4th. Here's x to the 4th. If I move x to the 4th to the left one, I still have the same number of zeros. What happens if I move it up 1? Huh. Interesting. Okay. At the beginning, I had asked you this question. When will a transformation impact the number of real zeros? And then we looked at some examples. And now I'm showing you a case where it does. I want you to be thinking about that. I want you to be thinking about that. I just told you this right here represented moving left 1. No impact. Up 1. Major impact. Down 1. Does it impact? Squishing it, compressing, stretching, flipping, whatever. How does it impact? That's what I want you to be thinking about. Okay? Have that in the back of your mind. You're smart people. I know you can figure this out. I want you to be having that in your mind. Thank you, thank you, thank you.